Hello, today we are going to discuss something which is very important in quantum mechanics point of view but has not been included in our syllabus. There are not many books of quantum chemistry in which these topics are included, but this topic will surely provide us with some additional benefits in understanding the wave function. First of all, we will discuss about the vector space. What do you mean by a space? A space is nothing but a region. Like this board is a two-dimensional space. It has a dimension along this direction and there is a dimension along this direction. Let this dimension be x, let this be y. So a vector space is nothing but a space which contains two sets of elements. What are these? The first set is of vectors and the second set is of scalars. Now you see these vectors are there. Suppose this is A and this is B, and certain laws govern over these vectors, such as the sum of any two vectors from this vector space must also be a vector which belongs to this space, must also be a vector which belongs to this space. Like the sum of these two vectors will be x vector. Also there is another law. If a vector is multiplied with any of the scalars, suppose A, then the resultant A must also be an element of this space. The sum of any two vector must be a vector which is an element of this space. If the vector is multiplied with any of the scalars, then the resultant must also be an element of this space. This is what we mean by vector space. Now you see this is a two-dimensional vector space. Now if we consider a infinite dimension vector space, then it will be known as a Hilbert space. A Hilbert space is an infinite dimension vector space which is complete. Now, what do we mean by complete? By complete we mean that there exists a Cauchy sequence. Now, what is a Cauchy sequence? Suppose there are some elements in this sequence. As the value of n increases, the difference between any two consecutive element decreases. The difference between any two consecutive element decreases as the value of n increases. A1, A2, A3, A5. Now you see at n equals to infinity, what will happen is that the difference between the two consecutive elements of this sequence will be 0. This is known as a Cauchy sequence. Let us consider an equation first. Suppose we have a two-dimensional vector space. Okay, with x, y. So in this two-dimensional vector space, let us consider equation. The resultant of two vector is 0. Now you see that there may be two possibilities when both a and b is equals to 0, or this may be another possibility. In this case, where a and b both are 0, then these vectors are known as linearly independent vectors. Whereas in this case, when a and b are non-zero, then a can be given in terms of b. A can be written in terms of b. So this is these vectors, a vectors and b vectors, are known as linearly dependent vectors. Now you see, if a and b, if this equation is satisfied, and small a and small b, that is the scalars with which they are respectively multiplied, is 0, and for any value of a and b, or at any point, this equation is not satisfied, then we can say that these vectors are bases. Let me make it clear. Suppose there are two vectors a and b such that a plus bb is equals to 0, and now we are saying that this is not possible for any values of a or b. For any values of a or b, this is not possible. So the only possibility is a comma b must be equals to 0. If these are maintained, then the vector a and b are known as bases. And what is the dimension? The total number of bases, or total number of linearly independent vector present in this space, is known as the dimension of this vector space. These two vectors a and b will be called linearly independent if and only if these two criteria are maintained. Suppose from our elementary knowledge of vectors, we know the unit vector along x-axis is known as I cap, and unit vector along y-axis is known as j cap. So any vector, say u vector, say here it is 5, here it is 3. So any vector u vector can be given as the sum of I and j vector. right? Any vector in this vector space can be given in terms of the ij, but you see, for any value of ai plus bk, let's suppose a is equals to 0, and this is only possible, this will only be possible when both a and b will be 0. If both a and b will be 0, then here it is, it will be 0, but without it, there is, for no value of a and b, this will be satisfied, this equation will be satisfied. So we can say that I and j are the bases of this two-dimensional vector space, and a vector in this space can be represented in terms of the bases. Now, what is a scalar product? It is important to know about the scalar product. Suppose there are two vectors in this vector space, one is u, another one is, suppose v vector, which is here it is 5, sorry, not here, here it is 5 and here it is 6. So v vector is equals to 6i plus 5j caret, and u vector is equals to 5i plus 3j caret. Now you see, what is the scalar product of u and v? By scalar product, we represented it as u v. That means the projection of u on v is known as the scalar product between the two. The projection of u on v is known as the scalar product between the two. Similarly, if we perform a scalar product, then we will find that this into this plus this into this, but this into this, that means when we will be multiplying I into j, then what will happen is that the resultant will be 0, and thus it is not incorporated here. So the value will be 45. Now we are going to discuss function spaces. Suppose we have considered a particular interval a to b along x-axis. So there may be multiple number of functions which may operate in this region. Here we have considered only 3, but there may be many more. So all these functions which are actually operating in a particular interval are the constituents of the function space. The functions and vectors are analogous to one another, and one particular analogy can be made that we will discuss now. Suppose we take 3 points here in this axis, A1, A2 and A3. So their corresponding point will be F1, F2 and F3 will be somewhere here. So f of x can be given as the sum of f1 2 and f3. Similarly, g of x can be given as g1 plus g2 plus g3. Also, h of x can be given as h1 plus h2 plus h3. Now, we have seen in case of vector space that vector in a vector space is given as the in terms of the basis. This may be a vector space. This may be a vector in the vector space. This vector is given in terms of the bases. These are the bases. Here also you see, if these are vectors, then this must be the basis. So you see, here we have considered only 3 points, but there are infinite number of points. So this f of x can be given as the sum of infinite numbers or infinite elements. Similarly, this g of x can also be given as the sum of infinite elements. So is the case for h of x. Now, as there are infinite number of bases, so we can write it as it could be f of x. So for g of x, we can write it as it will be g of x, and for h of x, it will be now. What will be the scalar product in case of the function space? Scalar product. Suppose we want the scalar product of f and g, so it will be given by f of x. Now you see, both f of x and g of x are operating within the same interval. So this will have a real value. Now if this was the case, if this was the case, when the f of x and g of x are not in the same interval, that means their bases are not same. So their bases are different. So the integral will be 0. In that case, integral will be 0. If we consider only the normalized functions, then for normalized function, what will happen is that we have also mentioned earlier that by scalar product, we actually mean the projection of one entity. Suppose if we consider here we are giving the scalar product of two functions, we are actually considering the projection of the function f of x on g of x, on projection of function of f of x on g of x in this particular interval. So now what I was saying is that if you take the normalized function, then f square, that is the scalar product of function f with itself, will be this. Then what will be the projection of this function upon this function, upon itself? So obviously it will be 1, as we are taking here the normalized function. So the projection or the scalar product will be 1. Now our f dot g is actually a to b f of x, g of x dot dx is diverging. By diverging we mean the value of this integral is infinity. Now if the value of this integral is infinity, so we can say that the scalar product does not exist at all. So if the scalar product has to exist, then the value must not be infinity. F dot g must be finite. F dot g cannot be infinite. For f dot g being finite, what we need to do? We need to have the wave functions f of x and g of x to be finite. So you see, when we will be doing the scalar product of f with itself, then if f of x is finite, both are finite, then we will obtain 1 here. But if both are infinite, then the integral will be infinite as well. If both are infinite, the integral will be infinite. So the function must be square integrable. By this statement, we mean this integral must be finite. It must have a finite value. So a question now arises is that what is the use of all these things in quantum mechanics? One of the greatest discoveries of quantum mechanics is the dual nature. According to the dual nature, a matter can have both the particle and wave nature. Not can have, but has. A matter has both the particle as well as the wave nature. The particle nature enables us to locate a particle with accuracy in space, whereas wave nature, as the waves are spread out in space, so it is seen that the matter is delocalized. So to establish dual nature, the concept of wave packet was introduced. So now let us consider two waves, the blue one and green one. In this position you see good constructive interference between the two waves, that is the green one and the blue one, is taking place. Here also the constructive interference are taking place, but the extent is somewhat less. Similarly, the extent is much smaller here, and in this region only destructive interference are taking. As a result of this, function question appears something like this. This portion is where psi is not equals to 0 and in this portion psi is equals to 0, psi equals to 0. Now you see this is known as a wave packet. This wave packet now enables us to locate this matter in this region. That means the probability of finding that particle must be here. There is no probability of finding the particle. The probability is restricted to this region only. So this wave packet actually satisfies both the particle nature as well as the wave nature. Now you see this function only operates in this region, but outside this region this function is not operating, or the function is 0. The function is operating in this particular interval only. So it can be said that this function is an element of a function space. Since it is an element of a function space, so all the rules and all the laws of function space are applicable here. Just now we have seen that the functions which are an element of function space f of x must be finite. Similarly, this wave function psi must also be finite. Today, with the concept of function space, we have understood why the psi must be finite. In the previous video, we have discussed about the criteria which must be followed by a function so as to be known as a wave function. In those criteria, there was a point that the wave function must be finite. And today, we have learned why it should be finite. That's all for today, and I hope you will like this video, and I will try to post new things related to quantum chemistry and other parts of physical chemistry. Thank you. Goodbye.